Imagine a colossal, perfectly symmetrical eye staring up from the vast ochre expanse of the Sahara Desert.
Hmm.
It's not a natural pool. It's certainly not an alien landing site, though, full disclosure. Some have definitely guessed that. But a geological wonder so immense, it's clearly visible from Earth's orbit.
It really is striking from up there.
This, right here, is the Richat Structure, famously known as the Eye of the Sahara.
A very fitting name.
Okay, let's unpack this. Whether you've seen breathtaking images of it swirling across your feed, or maybe you're just hearing about it for the very first time, our mission in this deep dive is to, peel back its concentric layers.
Get right into it.
Exactly. We're going to explore what it truly is, how it defies common misconceptions, and why it's not just a geological spectacle, but actually a crucial archive of Earth's deep past and even early human history. We've taken your sources from rigorous scientific reports to some pretty intriguing historical accounts, and we're going to distill the most fascinating and foundational insights for you right now, bringing this mysterious wonder into sharp focus.
And that journey of discovery itself, even for something known locally for, well, millennia, is itself quite captivating.
Oh, really? How so?
Well, its sheer scale and, its isolated location meant that it took a completely new vantage point, specifically the nascent era of human spaceflight, for it to truly capture global scientific attention.
Right, from space.
Exactly. And that sparked the investigations that brought us to today's understanding. It's a remarkable example of how a shift in perspective can fundamentally change what we see and what we investigate.
A new way of seeing something ancient.
Precisely.
So, formally introducing our star today, it's the Richat Structure. It's often also referred to by its local name, Richat.
Richat. Yeah.
You'll find it nestled deep within the Adrar Plateau of Mauritania, which is a pretty rocky, isolated expanse, even by Sahara Desert standards.
Very remote.
And when we talk about its scale, we're not talking about something you can just stroll across in an afternoon or even like a week. This thing spans a staggering 40 to 50 kilometers in diameter.
That's huge.
Yeah, that's roughly 25 to 30 miles across, with a central dome that's almost 20 kilometers wide.
20 kilometers for just the dome.
To give you a real sense, that's bigger than many major cities. It's this colossal size that makes it so striking, earning it nicknames like a vast bullseye or that giant eye.
You can see why.
And from ground level, you simply can't see the whole picture. Its extraordinary, symmetrical nature is almost impossible to grasp fully.
Right, you're just too close. It's too big.
Exactly. You could be standing on one of its rings and not even realize you're part of such a magnificent, perfectly formed circle. It's just too vast.
You just see maybe a ridge in the distance.
Here's where it gets really interesting. It's discovery. Now, while local populations have known about it for millennia, navigating by its features, its existence remained largely unacknowledged by the broader scientific community until, well, a pivotal moment in June 1965.
It's a fascinating paradox, isn't it? This whole idea of discovery.
How do you mean?
Well, you have local communities who have lived with and navigated by this feature for untold generations. They possess a deep, practical knowledge of their environment. They knew it intimately.
Right, it was just part of their world.
Exactly. But the formal scientific community, based largely in the Western world, remained largely unaware until 1965. That's when American astronauts aboard the Gemini 4 space mission, as they orbited Earth, were quite literally captivated by its distinct appearance.
They just saw it out the window.
Pretty much. They saw this enormous, perfectly circular feature, a bullseye staring up from the desert, and it stood out unmistakably against the vast, relatively featureless expanse of the Sahara. You couldn't miss it from up there.
Wow. What was their immediate reaction, do we know? Did they have any idea what they were looking at?
That's a great question, because their initial speculation was quite telling. They thought it might be a meteor crater.
Okay. That makes sense, visually.
It's a logical inference, absolutely, given its striking circularity and immense size. But this initial observation wasn't just a fleeting curiosity or, a pretty picture for the folks back home. No, it actually spurred detailed investigations back on Earth, and it really cemented its recognition as a significant navigational landmark for space crews on subsequent missions.
So astronauts started using it to figure out where they were.
Essentially, yes. From that moment on, it became a standard reference point. Okay, there's the eye. We know where we are over Africa. And this really highlights a crucial aspect of scientific inquiry, which is the power of new vantage points. Unexpected observations from a novel perspective, like Earth orbit, can reveal previously unappreciated terrestrial phenomena.
Seeing the Earth in a new way.
Precisely. The Richat Structure's prominence from space transformed it from a regionally known geological feature into a subject of global scientific interest. It demonstrates how advancements in observational technology, even something as fundamental as simply going higher, can fundamentally drive Earth science research. It truly underscores that what is discovered by one group may simply be a recontextualization or a new way of understanding something that has always been present and known to others, but perhaps understood in different contexts.
So the locals knew it, but science discovered it from space.
In a manner of speaking, yes. And the inability to fully grasp its nature from the ground level, as you noted earlier, almost certainly contributed to this scientific oversight until that unique aerial perspective was gained. It's a testament to how sometimes, to understand something truly massive and complex, you have to literally step back and see the bigger picture.
Fascinating perspective. That's a profound point. So we've grasped its immense scale and how it kind of burst onto the modern scientific scene. Now, let's truly dive into its distinct physical characteristics. When you see those images from above, what immediately strikes you is that incredibly symmetrical bullseye appearance. It's just mesmerizing.
It really is. Hard to look away.
And what you're actually seeing are these distinct circular ridges. Geologists call them cuestas, essentially. They're asymmetrical ridges, almost like natural stair steps, where one side slopes gently and the other is much steeper.
Right, like a tilted layer of rock sticking out.
Exactly. These cuestas have been meticulously sculpted by erosion, forming perfect circles. And you can actually see an alternating pattern of dark and light-colored rocks that create that hypnotic bullseye effect.
That adds to the visual impact, definitely.
The outermost rings, just to give you a sense of just how big this is again, measure about 40 kilometers across.
40 kilometers.
And right at the very center, there's a peak that rises approximately 400 meters above the surrounding desert floor. It's like a giant, perfectly concentric target laid out on the desert.
A geological bullseye. So, to truly understand what we're looking at, we need to delve into its geological composition. The Richat structure isn't uniform. It's actually a complex mosaic composed of a diverse array of rocks, varying significantly in both age and composition.
Okay, so not just one type of rock.
Not at all. The prominent concentric rings, for instance, are primarily formed from ancient layers of sedimentary rocks.
Sedimentary. So laid down by water or wind over time.
Exactly. Rocks formed from the accumulation and compaction of sediments over vast stretches of time. And these layers date back to the late Proterozoic period, which is incredibly old. We're talking around 600 million years ago.
600 million years. That's mind-bogglingly old.
It really is deep time. And these layers extend into the Ordovician period, roughly 485 to 443 million years ago.
So these ancient layers were laid down over hundreds of millions of years and then somehow revealed.
Precisely. Within these sedimentary layers, you find incredibly resistant rocks like quartzite, which is a very hard metamorphic rock, along with things like sandstone and limestone.
Quartzite, okay. That sounds tough.
It is, and it's actually the quartzite that is largely responsible for those distinct prominent ridges you see. Because of its remarkable resistance to erosion, think of it like a natural shield against the elements.
Right, it holds up better.
Exactly. In contrast, softer sedimentary rocks, such as shale and other types of sandstones, are much more susceptible to erosion, so they form the valleys or depressions between the ridges, where they've been worn away more easily over time.
Ah, okay. That makes sense for the rings. But what about the center?
Right. The story doesn't end there. As you move towards the inner rings and the central core, you encounter a completely different set of materials. Various igneous rocks.
Igneous, from magma. Like volcanic rocks.
Formed from cooling molten material from deep within the earth, yes. Their diverse presence is really telling. We find things like rhyolite, often associated with explosive volcanic activity, gabbro, which cools slowly underground, even kimberlite.
Kimberlite, like where diamonds come from?
The very same type of rock, though no diamonds reported here. And basalt, common in volcanic areas. All these different types tell us a clear story. This entire structure has deep roots in Earth's fiery interior.
Wow.
Research points to an underlying alkaline igneous complex that contributed to its formation, dated specifically to the Cretaceous period.
Cretaceous. So, dinosaur times. Around 100 million years ago.
Roughly, yes. Between 145 and 66 million years ago. And right at the very center, there's another interesting feature. A kilometer-scale siliceous breccia.
Breccia. What's that?
That's essentially a rock body made of broken rock fragments, angular pieces that have been fused or cemented together, often by heat, pressure, or mineral solutions.
So a mix of broken bits glued together in the middle.
A good way to put it.
So I've got sedimentary rocks from ancient oceans or lakes and igneous rocks from Earth's deep, molten interior. It's like a geological layer cake that's been sliced open and pushed up.
Precisely. A fantastic analogy. And what's truly fascinating here, adding another layer to this incredible story, is the evidence of past water presence.
Water in the middle of the Sahara.
Yes. Within deposits of fine-grained gravel and sandstone found throughout the structure, scientists have discovered freshwater fossils. Things like fish bones, mollusks.
No way. How old are those?
They date back as far as 15,000 years. This offers a powerful hint at a dramatically different past environment for what is now one of the driest places on Earth.
So 15,000 years ago, it wasn't a desert there.
It paints a picture of a much wetter, more hospitable Sahara, supporting freshwater life that once thrived in this region. Rivers, maybe lakes.
Incredible. That changes everything.
It does. Now, all these different rock types, with their varying resistances to the elements, are absolutely crucial to understanding the Richat's distinctive appearance. That stunning circular pattern is a direct consequence of a fundamental geological process known as differential erosion.
Differential erosion. Okay, break that down.
Imagine you have a stack of different materials, some hard, some soft. If you expose them all to wind and rain, the softer ones would wear away much faster, right?
Yeah, makes sense.
That leaves the harder ones standing proud, sticking out. That's differential erosion on a grand scale. It's the gradual, preferential removal of softer rock layers by wind and water, which then leaves behind the harder, more resistant layers in that spectacular circular pattern we see.
So the quartzite ridges stick out, and the softer shales get carved out into valleys between them.
Exactly. The varying resistance of these different rock types is fundamental to this sculpting process. This makes the Richat structure a compelling, large-scale natural laboratory for studying erosional processes. It's like a textbook example of how relentless forces like wind and water, acting over millions of years, can sculpt a complex geological history into a visually striking landform,
Revealing the layers beneath.
revealing the underlying stratigraphy and rock properties. It's a masterclass in Earth's slow-motion artistry.
So what does this all mean? We've got this giant eye, rocks in all different ages, evidence of ancient water, all shaped by this incredible differential erosion. Let's get to the crux of it. The scientific consensus on how this incredible formation actually came to be.
Okay, the bottom line.
Yeah, geologists have pretty definitively classified the Richat structure as an uplifted geological dome. More specifically, they call it a domed anticline. Can you break that down for us?
Absolutely. So an anticline is basically an arch-like fold in rock layers, where the oldest layers are in the core of the fold. Imagine bending a stack of paper upwards in the middle. That arch is an anticline.
Okay, like an arch.
Right. And a domed anticline is simply an anticline that's circular or dome-shaped in 3 dimensions, rather than just a long ridge. Think of pushing up the very center of a layered cake. The layers would arch upwards and outwards, forming a dome.
Got it. So the ground itself bulged upwards in a circle.
Exactly. The formation of this dome is believed to have occurred approximately 100 million years ago.
Back in the Cretaceous period when those igneous rocks formed.
Precisely. This timing is actually quite significant as it coincides with the massive geological forces involved in the breakup of the supercontinent Pangaea. Africa and South America were actively pulling apart around then, causing a lot of stress and magmatic activity in the crust.
Right, continents ripping apart.
The most widely accepted theory posits that molten rock, or magma, from deep within the Earth's crust began to intrude upwards. Now, critically, this subsurface igneous intrusion did not erupt to the surface like a volcano.
Ah, that's key. It stayed underground.
Yes. Instead, it pushed up and deformed the overlying sedimentary rock layers, those ancient Proterozoic and Ordovician rocks we talked about, causing them to bulge upwards and outwards, creating that distinctive dome-like formation we see today.
It just lifted everything up.
Exactly. And the concentric circles, those stunning rings, are thought to have originated from fractures that developed in the crust as a result of this significant upward pressure and uplift event. Think of it like cracks forming in the crust as it was stretched and pushed upwards.
Like stress fractures on the dome.
That's a good way to visualize it.
So a giant bubble of magma pushed up the Earth's crust, but never broke through.
That's fascinating. What's the definitive evidence for this kind of subsurface push rather than, say, a huge volcanic eruption? That's a crucial distinction, And the evidence for this magmatic origin, this intrusion, is quite concrete. We see a widespread presence of various igneous rocks. Those rocks formed from cooled, molten material like rhyolite, gabbro, kimberlite, and basalt found throughout the interior of the structure.
Not just on the surface.
Right. They aren't surface volcanic flows. They are found within the structure in ways that suggest they solidified underground before erosion exposed them. We also find features like basaltic ring dikes.
Ring dikes.
Essentially vertical or near vertical sheets of cooled magma that intruded into fractures, often forming circular or arc-like patterns around the central intrusion. We also see kimberlitic intrusions and alkaline volcanic rocks, all pointing to this internal magmatic process.
Okay, lots of different igneous fingerprints.
Exactly. Research specifically points to that underlying Cretaceous alkaline complex as the driving force. Even the central breccia body, that mix of fused rock fragments we mentioned earlier.
Yeah, the glued together bit.
Its formation is thought to be linked to the hydrothermal activity, hot water circulating, associated with that initial hot magmatic activity deep below. Maybe some dissolution and collapse of overlying rock, facilitated by that heat and fluid flow.
So the evidence points strongly inwards towards something pushing up from below.
Correct. But the story doesn't end with the uplift. That just created the basic structure. Following this initial geological event, the dome was subjected to millions upon millions of years of relentless erosion by wind and water.
And that's where differential erosion comes back in.
Absolutely. This is where that process truly plays its crucial sculpting role. It preferentially removed the softer rock layers, those less resistant shales and sandstones, while the harder, more resistant quartzite layers remained,
Creating the ridges and valleys.
creating the distinct circular pattern of ridges and valleys we see so clearly from space. It's a classic textbook example of how Earth's surface sculpts features over vast timescales, revealing what lies beneath.
What?
And here's a fascinating detail. Persistent northeasterly winds in the Sahara, blowing sand away, play a crucial role in keeping much of the dome free from accumulating sand.
So the wind helps keep it exposed.
Exactly. It continually exposes these various layers of rock, ensuring that the eye remains visible and distinct, preventing it from being buried by the shifting desert sands over time.
Nature's own cleaning crew.
In a way, yes. So if we connect this to the bigger picture, the visible eye isn't solely the result of one process. It's a profound and continuous interplay between deep-seated endogenic or internal forces
Like the magma pushing up.
and exogenic or surface processes.
Like the wind and water erosion.
Precisely. The uplift, driven by molten rock, first created the foundational dome, bringing older rock layers from deep underground closer to the surface. Subsequently, differential erosion, a surface process, meticulously carved out the concentric rings, patiently revealing the internal structure over millions of years.
The collaboration between inside and outside forces.
A perfect way to put it. This dynamic interaction illustrates a fundamental principle in geology. Earth's surface features, especially those as grand as the Richat Structure, are often the complex result of long-term, multi-stage processes. They involve internal forces like plate tectonics and magmatism that build and deform the crust, and external forces like weathering and erosion that sculpt, strip away, and reveal these underlying structures. The Richat Structure serves as an exceptional natural laboratory for understanding this intricate, millennia-long dance between Earth's interior and its surface. It showcases how deep Earth processes leave their enduring mark on the landscape, which is then further shaped by surface phenomena. It's truly a testament to the planet's slow, powerful, and continuous transformation.
An incredible story written in rock. It's really no surprise that such a unique and visually striking formation would spark all sorts of wild theories and initial curiosities, right?
Oh, absolutely. Anything that looks this unusual is bound to capture the imagination.
When something is so mysterious from afar, the human imagination tends to run wild, trying to make sense of what it sees. So here's where it gets really interesting. Addressing the most prominent misconceptions about the Richat Structure's origin. Let's tackle the big one first.
The meteorite impact hypothesis, yes, that was a very logical initial inference.
Because it's round.
Exactly. Its striking circular symmetry led many, including those early Gemini astronauts we talked about, to believe it had to be a giant impact crater formed by a meteor hitting the Earth.
Makes perfect sense at first glance.
It does. However, what makes this a compelling case study in the scientific method is how that initial hypothesis was rigorously tested and ultimately definitively disproved through extensive scientific studies and, crucially, on-the-ground research.
So seeing wasn't believing in this case.
Not quite. This is fundamental to the scientific process. You don't just accept an initial interpretation, no matter how appealing or visually compelling it might seem. Science demands evidence, specific evidence.
Okay, so what specifically did scientists look for that would confirm a meteorite impact, and what did they find, or rather not find, at the Richat Structure?
Excellent question. Scientists looked for very specific diagnostic markers, the geological fingerprints that a massive meteorite impact leaves behind. Things that only happen under those extreme conditions.
Like what?
For example, a key piece of refuting evidence is the complete absence of shock-altered rocks. Meteorite impacts generate immense instantaneous pressure and heat far beyond anything found in typical geological processes on Earth.
Okay.
This intense shock leaves behind distinctive shock metamorphic features in the rocks, things like shattered mineral grains, specific high-pressure mineral forms, or unique melt textures. These crucial indicators are notably and consistently absent in the Richat structure. They've looked hard, they're just not there.
No shocked rocks.
Got it.
What else?
Secondly, true impact craters, especially large, complex ones, often exhibit a central peak or a central peak ring. This is formed by the elastic rebound of the rock beneath the impact point, kind of like how water splashes back up when you drop a stone in it.
Right, I've seen pictures of craters with those central mountains.
Exactly. The Richat structure does not possess such a feature. Its center is actually part of the overall uplifted dome, not a rebound structure.
Okay, no central peak.
Furthermore, there's no prominent evidence of impact melter. You'd expect a large impact to generate a significant amount of rock melted by the intense heat of the collision. Again, this isn't found in the quantities or forms expected for a crater of this size.
No big melted zone.
Right. And finally, maybe the most fundamental point. The Richat structure's overall geological form is that of an uplifted dome. It's a structural high. An impact crater, by its very nature, is a depression, a hole in the ground.
So it's a wrong shape, fundamentally. It bulges up, not down.
Precisely. And crucially, remember all those igneous rocks we discussed.
Yeah, the rhyolite, gabbro, all that stuff from below.
The widespread presence of those rocks, formed from Earth's internal molten material, along with complex magmatic intrusions like the ring dikes, strongly points to an internal magmatic origin rather than an extraterrestrial impact. The geology screams, formed from below, not hit from above.
Okay, that seems pretty conclusive. Case closed on the impact theory.
Scientifically, yes. This process highlights how scientific understanding evolves through evidence-based inquiry. Specific geological indicators provide definitive answers, even when initial visual interpretations might suggest something else. It underscores the importance of moving beyond superficial resemblances to detailed, verifiable evidence found on the ground.
Right. Don't judge a geological feature by its cover, essentially.
A good way to put it. Now, beyond the meteorite theory, there's another persistent fringe theory. One that grabs headlines now and then.
Oh, I think I know where you're going with this.
The claim that the Richat structure is the site of the legendary lost city of Atlantis.
Atlantis. Okay, I definitely heard this one. How does that connection even get made?
Well, proponents of this theory often point to, again, superficial similarities between the Richat structure's concentric, circular shape and size and Plato's ancient descriptions of Atlantis.
Plato, the philosopher.
Yes. In his dialogues, Plato described Atlantis as a city built on alternating concentric rings of land and water.
Okay, I see the visual connection. Rings.
Exactly. Some proponents even cite the presence of red, white, and black stones in the Richat area, aligning with Plato's description of materials used in Atlantis' construction, and they point to the evidence of a wetter past, suggesting a past island environment.
So people are really trying to connect the dots based on visual cues from the structure and comparing them to an ancient philosophical text. What's a scientific response to something like that?
Well, it's really important to understand that this isn't a scientific debate. It's firmly in the realm of popular misconception or pseudoscience.
Not taken seriously by geologists or archaeologists.
Not as a plausible identification of Atlantis, no. The Atlantis theory continues to circulate, often online, despite overwhelming scientific consensus against it, because it relies heavily on those superficial visual parallels. It appeals to that deep human desire for romanticized, lost civilizations.
Finding magic in the landscape.
Perhaps, but scientific counterarguments demand tangible, verifiable evidence. And the fundamental refutation lies in the complete absence of any archaeological proof to support the existence of an advanced city or civilization at the site.
No ruins. No pottery from a complex society, nothing.
Nothing remotely like what Plato described or what you'd expect from a major Bronze Age or earlier civilization, while primitive stone tools and pottery shards, which we'll discuss more later, have been found.
Right, the Acheulean tools you mentioned.
Exactly. Those are distinctly different from any evidence of a sophisticated, technologically advanced lost city with canals, temples, and harbors as described by Plato. There's just no comparison.
Okay, zero archaeological evidence for a city. What else?
Furthermore, the Richat structure is unequivocally a geological dome, an uplifted landform. It's a mountain, essentially, that's been eroded. It's not a depression or a site conducive to the kind of city construction Plato described, let alone one that sank.
Right, Plato said Atlantis sank beneath the waves. This is a landform sticking up in the middle of a desert.
Precisely. The geology is completely wrong. There are no indications whatsoever of submerged ruins, advanced infrastructure, or any artifacts consistent with a highly developed ancient civilization that supposedly vanished. And maybe most importantly, Atlantis itself is widely regarded by historians and archaeologists not as a historical place that ever physically existed, but as a philosophical allegory or myth created by Plato in his writings.
He made it up to make a point.
That's the overwhelming scholarly view. He used the story of Atlantis, likely inspired by various real events or places, but ultimately fictional, to convey philosophical concepts about ideal societies, hubris, and divine retribution. It wasn't intended as a geography lesson.
So comparing a geological feature to a philosophical myth based on looks alone.
It serves as an excellent illustration of the distinction between speculative theories driven by visual resemblances or cultural narratives and scientific hypotheses that must be rigorously supported by empirical data and be consistent with established geological and historical principles. It highlights the scientific community's commitment to evidence-based conclusions, even when the truth is perhaps less sensational than popular myths.
Facts over fantasy.
Essentially, yes. And just to quickly cover bases, there are other less prominent fringe theories.
Oh, like what?
Some suggested a direct volcanic eruption forms the eye, but as we discussed, while magmatic activity is central to the uplift,
Right, the push from below.
the lack of a prominent volcanic crater or other definitive surface eruptive features makes a direct volcanic eruption as the primary sculptor of the eye itself very unlikely. The molten rock pushed up but didn't really erupt in a way that would form a classic volcanic caldera or cone matching the structure.
Okay, so not a volcano crater either. Anything else?
And then, perhaps the most outlandish, and certainly without any scientific backing whatsoever, is the myth that the Eye of Sahara is some kind of landing ground for alien ships or an alien artifact.
Ah, the alien theory. Knew that had to be in there somewhere.
Such theories, unsurprisingly, lack any credible scientific or empirical evidence. They are purely in the realm of speculative fiction, likely born simply from its unique, almost otherworldly appearance from space.
It does look pretty weird from orbit, gotta admit.
It certainly does, but weird doesn't automatically mean alien. It means interesting geology.
Okay, so we've firmly established that the Richat structure is a geological dome, sculpted by Earth's powerful internal and external forces, and we've confidently debunked the major myths: no meteor impact, no Atlantis, no aliens.
Correct, on all counts.
But it's so much more than just a geological wonder, isn't it? You mentioned it's also an incredible window into human history, and it serves as a crucial scientific landmark. Okay, let's unpack this aspect, starting with its archaeological treasures.
Absolutely. This is where the story gets another fascinating layer. The Richat structure and its surrounding region are not only a geological marvel, but also a site of immense archaeological interest. It shows clear signs of ancient human activity spanning vast periods of time.
Ancient humans lived here, in this now barren area.
They certainly spent significant time here. Archaeologists have unearthed exceptional concentrations of Acheulean-era stone tools.
Acheulean, those are the really old ones, right? Hand axes?
Exactly. Characteristic triangular hand axes, scrapers, tools like that. They've been found in the dry riverbeds, the wadis around the structure, and these artifacts date back between a staggering 1.2 million and 200,000 years ago.
1.2 million years.
Yes, indicating the presence and sustained activities of early human ancestors, specifically Homo erectus groups.
Wow. Homo erectus, right here.
And the discoveries don't stop there. Further findings include even older pre-Acheulean stone tools, pushing the timeline back further, as well as Middle Stone Age Aterian stone artifacts.
Aterian? What's that?
Those were produced by early modern humans, Homo sapiens, and they date from approximately 145,000 to 29,000 years ago. They're known for distinctive stemmed or tanged points.
So a long, long history of Different human groups using this area.
A very long history, and these weren't just passing visits. These were places early humans repeatedly used for specific activities.
How do we know that?
Well, excavations have even revealed large piles of stone flakes, the debris left over from making stone tools. Lithic debitage, archaeologists call it.
Workshop areas.
Precisely. This strongly suggests that the area was repeatedly visited specifically for the purpose of shaping and sharpening tools. And guess what they're using?
Let me guess.
The quartzite.
You got it. The local quartzite outcrops, the very same hard rocks forming the ridges of the Richat structure, served as a readily available, high-quality raw material source for these early inhabitants. They were using the geology around them to survive and thrive.
That's incredible, using the eye itself to make their tools. In a sense, yes. Now, what's truly fascinating here, and connects back to something we touched on earlier, is the paleoclimate implication.
Right, the freshwater fossils. How does that tie in with the tools?
Well, the presence of these ancient stone tools indicating significant human activity over long periods, alongside those freshwater fossils and related plant material. Finding all that in what is now an incredibly arid, hyper-desert environment presents a significant juxtaposition.
It seems impossible today.
It does. But the existence of these fossils and the evidence for sustained human occupation strongly imply a dramatically different paleoclimate. It points to a past environment that was much wetter and more hospitable.
The Green Sahara.
Exactly. It's consistent with what scientists call the African humid period, or periods, really. One major one lasted roughly from about 15,000 to maybe 5,000 or 8,000 years ago, though there were earlier wet phases too. This indicates a major environmental transformation of the Sahara from a landscape potentially featuring rivers, lakes, and grasslands into the vast desert we know today.
Mind-blowing to think about.
It truly is. The Richat Structure, therefore, transcends its purely geological significance to become a vital archaeological and paleo-environmental site. It offers a unique window into past ecosystems and the adaptive strategies of early human populations as they navigated these dramatic environmental shifts over hundreds of thousands, even millions of years.
So the tools and fossils tell a story of climate change and human adaptation.
Precisely. These archaeological findings provide critical data for understanding early human evolution and migration patterns, particularly out of Africa. How did they use and move through regions like the Sahara when it was a green corridor? How do they interact with changing environments? Thus, the site functions as a natural archives that allows interdisciplinary researchers, geologists, archaeologists, paleoclimatologists to reconstruct past climates, human behaviors, and the coevolution of life and landscape over vast timescales. It's a place where Earth history and human history are deeply intertwined.
Amazing. Is there anything else besides tools?
Yes, indeed. The landscape also features thousands of ancient stone burial mounds, tumuli of various styles. They often line the protruding land dikes or ridges within the structure.
Burial mounds. Whose? How old?
Each one is a silent sentinel to untold human stories. Unfortunately, their specific ages and cultural affiliations are yet to be definitively established through systematic excavation. That's a big area for future research.
Thousands of them, though. That suggests significant population or long-term use.
It certainly implies more than just fleeting visits during certain periods. And if that wasn't enough, several rock art sites have been identified within and around the structure.
Rock art. What does this show?
It depicts a range of its subjects, things like horsemen armed with javelins, two-wheeled chariots, various animals like bovids, cattle, elephants, giraffes, animals you wouldn't find there today.
Definitely not elephants in the Sahara now.
Yeah.
More evidence of a different climate.
Absolutely. Alongside these depictions are enigmatic ancient Libico-Berber inscriptions, an early script used in North Africa. These aren't just ancient doodles. They're vivid snapshots of a once thriving ecosystem and the vibrant cultures that inhabited it, telling us stories of an ancient Sahara that dramatically contradict our modern perception of it as an empty wasteland.
Wow. So much history packed into one place. It's incredible to think of this one structure holding so much history, both geological and human, like a living museum of Earth's past.
That's a great way to describe it.
But the Richat Structure's significance extends even further, right, into its role as a premier scientific landmark itself.
Yes, absolutely.
Its conspicuous visibility from space, as we discussed, made it a renowned landmark for space crews since the earliest Gemini missions in the 1960s. NASA astronauts first captured its image in 1965. But it's gone far beyond just being a pretty picture from orbit, hasn't it?
Indeed, it has. Beyond its initial visual appeal and use as a navigational marker, the structure has been a continuous subject of scientific debate and rigorous research for decades now.
What has studying it taught us?
It has significantly contributed to our understanding of fundamental geological processes, things like geological dome formation, the intricacies of complex erosion processes, especially differential erosion on a massive scale, and the broader geological history and evolution of the Sahara Desert itself.
So it's a key site for understanding Earth science principles.
Definitely. And this raises an important question. How did those early basic astronaut observations evolve into such sophisticated scientific application? It wasn't just looking out the window anymore.
Right. How do scientists study it in detail now,
Yeah.
especially being so remote?
Well, this is where technology comes in. It really revolutionized how we study Earth, particularly remote places like this. Advanced remote sensing technologies have been absolutely crucial.
Remote sensing, satellites and stuff.
Exactly. Take something like the Shuttle Radar Topography Mission, or SRTM. That flew on the space shuttle in 2000. It didn't just give us pretty pictures, it used radar to create incredibly precise, three-dimensional measurements of the Earth's surface topography.
Like a super detailed 3D map from space.
Pretty much, yes. Allowing scientists to see subtle elevation changes across the entire Richat structure, map ancient riverbeds now buried by sand, analyze the slopes of the cuestas, and even track the subtle shifts of sand dunes around it. All crucial for understanding its formation and ongoing evolution.
Okay, so radar can see the shape. What else?
Other technologies, like the Landsat series of satellites, provide multispectral images. They capture light in different wavelengths, including infrared. This allows geologists to identify different rock types based on their unique spectral signatures, how they reflect various wavelengths of light differently.
So you can tell quartzite from shale from space, basically.
To a significant degree, yes. It helps map out the geology over large areas quickly. And then there are things like X-band and C-band interferometric radar. These radar systems can sometimes penetrate through thin layers of dry sand, revealing underlying geological features or variations in moisture that are hidden from the naked eye or optical satellites.
Peering beneath the sand. That's cool.
It is. So the unique vantage point from space, initially a source of pure fascination, became an indispensable tool for detailed geological investigation. Remote sensing allows scientists to analyze the structure's complex features, its different rock layers, and its environmental interactions like those wind patterns and sand dunes in a way that ground-based studies alone simply cannot achieve, especially given how remote and challenging the environment is to work in.
Right, much easier than trekking across 50 kilometers of desert for every measurement.
Considerably. The Richat Structure, therefore, serves as an exemplary case study demonstrating the powerful synergy between space technology and terrestrial geology. It illustrates how advancements in remote sensing have revolutionized Earth sciences, transforming what was once a visual anomaly seen by astronauts into a critical site for understanding fundamental planetary geological processes and the dynamic interactions shaping our world.
A perfect lab observed from orbit.
It represents a profound shift from mere observation to detailed, data-driven analysis from orbit. And given this unique scientific value, it has been formally recognized and designated as an IUGS. That's the International Union of Geological Sciences Geological Heritage Site.
Wow, an official World Heritage Site for geology.
Yeah.
That's quite an endorsement from the international scientific community. So what's next for the Richat Structure? Are there still mysteries to unravel there?
Oh, absolutely. There always are in science. Recognizing its immense scientific and geological importance, the Richat Structure gained protected status in 2022.
Protected. How so?
It's aimed at preserving its unique geological and archaeological value for ongoing studies and future research, preventing destructive activities. It's a crucial measure.
Good. So what are the open questions?
Well, despite significant progress, some aspects of the Richat Structure's igneous and sedimentary components, their intricate interrelationships, and their precise origins remain, shall we say, enigmatic. There's still debate about the exact mechanism.
Still fine-tuning the details of how it formed.
Exactly. For example, further ongoing geophysical studies, maybe using seismic waves or gravity measurements and detailed geochemical studies of the rocks, combined with continued field observations, are essential to further unravel these complexities, particularly concerning the precise mechanisms of the magma's intrusion and the detailed formation process of that central breccia.
Still more digging to do, literally and figuratively.
Definitely. And of course, there's the human stories still waiting to be fully told. Future research endeavors could profitably focus on those thousands of stone burial mounds found along the land dikes.
The tumuli.
Yes, they remain largely unexcavated. Their systematic excavation could provide crucial insights into their age, the burial practices, and the human cultures that created them, shedding much more light on the people who once called this transformed landscape home. The eye truly still holds many secrets, both geological and human.
Plenty more for future deep dives then. Hashtag tag tag outro.
So,
Bringing it all together. The Richat Structure, unequivocally an eroded geological dome, stands as this monumental testament to Earth's dynamic and interconnected geological processes. Its iconic Eye of the Sahara appearance is really the magnificent result of deep-seated geological uplift,
that push from below.
driven by magmatic intrusion that pushed up but never erupted. And then it was meticulously sculpted over millions of years by the relentless, patient forces of differential erosion.
Wind and water doing their work.
This grand natural formation serves as just a compelling illustration of how internal geological forces like the ascent of molten rock create foundational structures, which are then intricately shaped and revealed by external forces like wind and water over vast timescales. Far from being a mere curiosity or the subject of those fringe theories we debunked, the Richat Structure serves as a crucial natural laboratory.
Absolutely.
Yeah.
And its story, scientifically, is really a triumph of the scientific method in action. The systematic refutation of those alternative hypotheses, like the meteorite impact and the Atlantis theories,
Yeah, those are persistent.
they were. But their refutation underscores the rigor of the scientific process, which demands empirical evidence and consistency with established geological principles over, just superficial resemblances or speculative narratives.
Seeing isn't always the whole story.
It's a powerful lesson in distinguishing between compelling visual patterns, which our brains are hardwired to seek out and find meaningful, and the demanding rigor of scientific evidence gathering and testing.
Mm-hmm.
And beyond its geological marvel, the site holds that profound archaeological importance. It provides a tangible window into the lives of early human populations and the dramatically different climates they experienced.
And green Sahara evidence.
Yes, the presence of ancient tools in freshwater fossils paints this vivid picture of a once fertile Sahara, making the Richat Structure a vital archive for understanding human migration, adaptation, and long-term environmental shifts. Its transition from just an astronaut's cool landmark to a protected geological heritage site really underscores its multifaceted scientific value and its enduring allure. It reminds us that there is always more to learn from the Earth beneath our feet, and also from the unique vantage point of space.
A story told from the ground and from the stars.
Well put. This raises, I think, an important question for you, the listener, to ponder. The Eye of the Sahara is not merely a visual spectacle, however stunning it is. It's a complex geological and anthropological narrative etched deeply into the Earth's surface over millions of years.
So the final thought is,
What more can this eye reveal about Earth's deep past, its climate fluctuations, maybe even its future? And what does it tell us about our own place, humanity's place, within its dynamic processes as we continue to look at it and learn from it, from both down here on Earth and way up there in space?